All right, so continuing on with the Mark II, we're taking a look at the Flamethrower now. So this one obviously was also inspired by Iron Man. If you look at Iron Man 1, the Mark I suit, he also has huge flamethrowers that he uses in the suit to actually escape the terrorist cave. Also, the Mandalorian has a similar style low profile flamethrower that he uses, and that's kind of probably more similar to the design that we're gonna be looking at. Both huge inspirations for kind of how the flamethrower is gonna work. So looking at how the system kind of started, it actually goes way back to even before the Mark I. When I started getting into building things in like middle school and high school, I watched a lot of YouTube videos on like people making things, and I came across Alan Pan, and he made a flamethrower that was punch activated. So that system used an accelerometer so that you could actually read the acceleration profile of a punch, and then use a microcontroller to actually open a solenoid valve and actually ignite the gas that came out from the valve. So I recreated the system exactly, and I got it to work. So that got me very comfortable building my own projects and kind of led me down a path of making a bunch of different things until I got to the Mark I, and that's when I wanted to incorporate that similar flamethrower design into the suit. So I basically took that design and distributed it amongst the entire Mark I arm. So it used an accelerometer still, used butane and a solenoid to release it. The control board was a custom PCB on the bicep, and it also used an arc lighter, except this one was now a custom arc lighter PCB that was embedded into the top of the forearm to better fit in the profile of the arm. Basically, everything's been redistributed amongst the arm. So the Mark I also took the acceleration of a punch to actually activate the flamethrower. I was able to get a really good test out of the Mark I. However, there's a part that's not really shown, and my hand may or may not kind of totally catches on fire at the end of it. It wasn't that safe, but like more importantly, it wasn't really consistent. The Mark I had a bunch of problems that affected the reliability of the system. The main two things were the actual igniter and the actual gas itself. So an issue with the arc lighter is that the high-speed flow from the butane can potentially disrupt the arc and kind of make it a bad environment to ignite the gas. Arc lighters are advertised to be like windproof and that kind of stuff. They no longer really hold up to that standard at very high speed flows. So what's happening with the arc lighter is that as you have your small input voltage from your standard power supply, it gets boosted up through a transformer in the arc lighter, and that transformer creates a very high voltage on the output. So the high voltage at the actual electrodes overcomes the dielectric threshold of the air, essentially meaning that the voltage is so high that the actual threshold required to allow charges to flow has been exceeded. So what happens now is that your air molecules being ripped apart into your positive and negatively charged ions, and those ions end up becoming a plasma channel that's a lot more conductive than the air itself, creating a throughput for the actual electrons to flow with your high voltage. And the arc itself is a super high temperature, and that's what you use to ignite the gas. However, if you have a very high speed flow of, like, let's say butane going over that arc, what you're doing is you're pushing those ionized air molecules out of the way. The arc is getting so stretched out that it's so thin now that it can't really ignite the butane because it's no longer in that thermal regime that it normally is at those shorter distances. Also, the high-speed flow can completely just blow out the arc, and then you have a very bad environment to actually reignite the arc, and it just doesn't really work. So that's one problem with the igniter. Also, another issue I had was that the butane that would come out sometimes would still be liquid. So what you have is that in your butane tank, you have your liquid butane and you have your gaseous butane at the top. That gaseous butane is pressurized at the vapor pressure to keep the butane mostly liquid. However, when you release it, what's happening is that the gas is allowed to expand throughout the piping system, and as it flows through your pipe, what you get is adiabatic expansion. Essentially, what's happening is all little butane molecules that are expanding and moving around, they bump into the walls of the pipe and lose energy. And as they lose energy, their general kinetic energy also decreases, and that is what temperature really is. It's just the kinetic energy of the molecules. So as you decrease the kinetic energy of the butane molecules, you're actually decreasing the temperature, and then decreasing the temperature makes the pipe super cold. So that means when you run the butane again, what you have is a very cold environment that the gas is trying to flow through. So it doesn't really expand because of the temperature as much anymore, and then you get more liquid butane coming out on your next attempt. And then the igniter has to ignite the liquid instead of just the gas, and that makes it even harder because your igniter is also having the flow problems. So there's kind of these two problems that are working together to reduce the effectiveness of the flamethrower. With the Mark II, the first problem I wanted to address was the actual igniter. So I went around looking for a couple of different systems, and I came across a glow plug. So what they're normally used for is diesel engines, where they sit right above the combustion chamber. You may be familiar with the standard 4-stroke engine that uses a spark plug, and those use gasoline. What happens is as you have your compression stroke, you use the spark plug to actually ignite the gas and create the explosion that does the actual power stroke. With the diesel engine, you have a different process. So the actual diesel gas itself is not as volatile as gasoline, which means that it's a lot harder to ignite. So what you have to do is create a super high temperature from the compression itself, and you can't really use any sort of external igniters. So what you have in your compression stroke is an actual adiabatic compression, and what's happening there is the actual air molecules have a lot less room to bounce around as you decrease the volume. They start moving around a lot faster, and that increase in the air molecule speed actually increases the temperature radically. Then when you release your diesel, it actually just ignites purely based on the temperature of the air that's being compressed. However, since that is very dependent on the actual temperature of the air being compressed, diesel engines have glow plugs as a way to preheat the chamber so that the actual air getting compressed is no longer affected so much by the cold outside and is actually preheated with the glow plug, and then when you do your compression, the diesel engine can start on its own. Really all that just to say that it's meant to get super hot. I did a bunch of tests with it allegedly through the window of my old apartment, and it worked really good as an igniter for that system. So you can see all these tests here We have a bunch of different flamethrower tests. All I really did was just put it in the path of flow, and then I would let the butane flow over it, and then it would ignite. It actually even worked when the butane was cold, which was surprising, but that's exactly what we wanted. However, as an igniter, it wasn't really perfect. So the main issue there is that the actual glow plug itself requires a ton of energy to actually get it to the temperature you want. So glow plugs are normally made out of very low resistance material that can actually heat up very quickly. So what happens is that as you create your voltage, you have a huge current flowing through your glow plug, and then that current gets transferred into actual heat energy. In order for it to actually work properly and heat up very quickly, you need a much larger power supply than what I would want to have for something like this. So with the arc lighter, all you have is a much smaller, like 5 to 6 volt power supply. With the glow plug, I was using like a 12 volt power supply and a boost converter to actually get the voltage high enough to create the current that we wanted flowing through the glow plug. So it worked well as a test bench setup, but it didn't really work well for a very low profile kind of sleek igniter that we wanted for the flamethrower. One of the things I used there too was like a wireless control board, very basic Arduino project, but it kind of laid the groundwork for the next wireless communication system that I'm using now. Also with those tests, one thing I noticed was that I was being limited by the actual butane flow. So the pressure of the butane gas is really only the vapor pressure of the liquid, which isn't so high compared to other gases like propane and MAP gas. So propane is stored at a lot higher pressure than butane to keep it liquid, and then MAP gas is stored at even higher pressure than propane to also keep it liquid. However, we also want a very visible flame. So with MAP gas, even though it's stored at a higher pressure, the high efficiency combustion of all those mixtures of gases creates a lot less visible flame because most of the actual soot particles are not present. And that means that the actual temperature may be higher, but your actual flame itself is going to be a lot less visible. So with propane, it's a less efficient combustion, and since it's stored at a higher pressure than butane, I'm going to get a longer gas flow, and I'm going to get a more visible flame than MAP gas, and we also get a higher temperature than butane. So propane is what I wanted to use now for the Mark II. I was able to do a bunch of tests with it as well just to make sure the system works. I kept using the glow plug to test the propane, but I was still not seeing the full flame propagation length that I wanted compared to the butane. So with the very first butane test in the Mark I, that was a huge flame. So looking to improve the flame length, I came across a bunch of people that actually put cornstarch in their flamethrower flow, and that actually enhances the flame propagation. So what you have is cornstarch, which is normally very tightly packed together, and you can't really get oxygen in between the particles there, so that when you try to ignite it normally, there's not really much oxygen for the actual ignition to occur. However, when you disperse it in the air, you have all these tiny little cornstarch particulates kind of floating around, and there's a ton of oxygen molecules also floating in between the cornstarch, and that creates a much better environment for your actual combustion. So throwing that into our propane flow, if we use the propane to kind of disperse our cornstarch particles, not only are we getting the propane to ignite, but they're also getting the propane to ignite the cloud of cornstarch, and then you're getting a huge propagation of your flow. So looking at how we actually want to inject cornstarch into our flow, one of the main things I was thinking of was using a Venturi system. And essentially that takes advantage of the very low pressure zone that's created when you have a high speed flow, and using that as a pressure differential to actually suck in something. Because you have to keep your Bernoulli constant, your dynamic pressure goes up, so then your actual static pressure has to go down. So thinking about that principle, if we apply it to like the cornstarch, what you do is you create a pressure differential around the cornstarch. You have your high pressure air on one side, you have your low pressure air on the other side, and that's gonna suck it into the low pressure zone because we have our high pressure pushing on our cornstarch. So using that principle, I just use like a basic T-bracket on my propane flow, and then I had a little tube of cornstarch, and as I ran the propane underneath it, it would create that low pressure zone and suck it in. But one thing I was noticing there is that the actual cornstarch itself wouldn't really flow that well. So it would work a couple of times, you'd get a couple of good flames, but the actual performance of the injection wasn't the best. Cornstarch itself is very hydrophilic, which means it bonds really well to water molecules because of the hydroxyl groups on the actual cornstarch molecules. And that results in problems with like the cornstarch particles wanting to separate, and it makes it a lot harder to get a very nice dispersion because they're kind of all clumping up as they absorb water. So what I added was aerogel powder, and that material is very hydrophobic, which means that it opposes the water molecules. So as you mix it with the cornstarch, the actual water absorption is a lot less, and it creates a very low friction zone between the cornstarch particles so they can slip past each other and get injected a lot more uniformly into the flow. So that works pretty good to get it to actually flow better. So after doing all these tests and kind of inching forward a little bit in progress, I kind of went a little crazy and kind of wanted to fix all the mistakes and kind of issues I've seen in the past and just make one design that addresses all of them. So that's kind of landed us here. So this is a new approach to the flamethrower that I'm trying out, currently working on optimizing. And really what it does is it takes all the problems we've talked about and targets them sequentially along the flow path. So in the Venturi zone, what's happening there is I'm actually decreasing the diameter by a factor of 2 in order to increase the flow velocity by a factor of 4, looking at the math. So not only are we gonna get our low pressure created from our high speed propane now, that constriction in diameter also increases the velocity to maintain the flow rate. And that means we have a much lower pressure compared to our original just T-bracket system that we had. So now that low pressure zone is connected to these offshoot pipes that connect to the cornstarch reservoir, and there I can put the cornstarch in and it can get injected in through those little tubes in the actual pressure differential that's created. Another issue I ran into while I was doing the test is that the actual pressure created from that flow would sometimes push out the cornstarch, and if you didn't have a cap or anything to seal it, you would lose cornstarch during the test. So thinking about that, I also added a little filter that prevents the cornstarch from going out, but still allows air to get sucked in as your Venturi effect happens, because if you seal the back of the cornstarch what happens is you create a vacuum and then your pressure differential is no longer as high because now you're fighting that vacuum pressure and it kind of reduces the effectiveness of the system. So next in the flow path is the preheater. So the preheater, what that targets is the actual adiabatic expansion that we talked about earlier, preventing the gas from getting so cold and affecting the actual consistency of the flamethrower. So what's happened there is that I'm using a very ferromagnetic tube material, and that means the material interacts a lot more with magnetic fields. So by putting an induction heater around the tube, use the circuit board to create very high frequency oscillating magnetic fields in that coil that then create eddy currents in the actual tube itself. So as those currents flow through the tube, you end up heating it up. Then you have a very hot chamber that the gas now has to flow through. So the actual induction heater itself is being optimized for another subsystem on the suit, so we won't worry about that right now. So moving on from the preheater, we now have our swirl chamber. What I designed is a double barrel swirl chamber that has an input and then these two pockets that actually create vortices of the gas as it flows in. So what happens is you suck in the air from that high speed, you create a very good mixture of oxygen and your actual propellant. So that means the actual chamber in there is a very good place to ignite our gas. So now I have the igniter actually in the swirl chamber taking care of the ignition. So just to make sure the basic flow dynamics of the actual flamethrower work, I just went back to temporarily testing with the arc lighter. Also, because the flow in the swirl chamber isn't as high speed and direct as it was on the old flamethrower, it's a lot better place to use the arc lighter because it's not as likely to get blown out. And then moving on from the swirl chamber, we finally have the nozzle. The nozzle isn't so crazy, it's not a really complex design part. It just has a couple of vent holes along the length of it to suck in more air as the flame goes out to better help with the actual combustion process and increase the efficiency a little bit. And one thing you might notice about a couple of parts in the sequence is that they're actually 3D printed out of titanium now. For those, I needed very high temperature resistant and very robust components. So I used DMLS technology, which is direct metal laser sintering. And that takes advantage of using a laser to kind of bind metal powder together to create whatever shape you want. And it allows for very complex geometries and very robust and strong parts. You can also imagine that I might use that to actually make the armor and all that kind of stuff because titanium is kind of perfect for that. So that's kind of where the flamethrower is now. And next I want to do a more in-depth flow analysis through the entire system because there's a lot that can be optimized and improved from the current designs that we have now. Also keep in mind, this part is only on the forearm. There's a whole bicep and chest piece component that's going to have to be added as well. That's going to be a whole nother aspect that needs to be improved and kind of designed. We'll get to that when we need to, but for now, that's kind of where things are.